Okay, good morning. So the topic of today, it's gravitational wave in linearized general relativity, linearized gravity around Minkowski, of course, flat spacetime. And this is somehow standard topic that you have already started something to some calculation and something to discuss yesterday during the tutorial. This is the topic that allows us to discuss the propagation of gravitational wave and effect on test masses, which these are then general results that generalize. So as you have started to discuss yesterday, in this approach, one makes the hypothesis that you have small perturbation around the flat metric or Minkowski, and this perturbation is encoded in this additional term to h mu nu in the metric. The hypothesis that is, so how small is a tensor with respect to another? This is a good question. The hypothesis that is behind here is that there's a global coordinate system. You can think about Cartesian coordinate for which every component of the perturbation is much smaller than the component of the Minkowski metric in that coordinate, which is, of course, equal to 1. And the idea is to go and linearize Einstein equation to linear order in H, okay, in the perturbation. So this is the theory, if you want, that allows you, or the approach that allows you to discuss weak gravity. We will show the weak metric, gravitomagnetic and gravitoelectric effects in the solar system, for example, and also gravitational wave propagation and the effect on test masses. So this, you can imagine that this is a good approximation when you are in any case, when you are very far away from the source and you are in such a situation. So formally, this linearized GR, you can think it of a field theory if you are a field theorist. Where the main field is, of course, this h mu nu, and where you have a background metric. Let me write this way. The gravitational field, it's H, and does not backreact on the background metric. And H is the main dynamical field, and the symmetries of this theory is symmetries that are inherited, or a subset of those that are inherited from general relativity, in particular infinitesimal coordinate changes, so diffeomorphism, which means that you can change H in this way, and nothing changes, where chi is the change of coordinate. It's a small parameter that is order h. It's a small parameter, and this is a small coordinate transformation. H changed in this way. This is the Lie derivative. If these are the component of a vector, this is the Lie derivative along that vector. And the theory is invariant for that. And another symmetry is, of course, Lorentz symmetry, so boosts and rotations, which go under the name of Poincaré. Poincaré group or Poincaré transformation. Now, I think you have seen yesterday during the tutorial how to linearize general relativity and have equation for H. So I'm going to skip that. It's a standard procedure that you also find in every book and you have seen in detail. The key thing is that you introduce a trace reverse metric, which is defined as H minus trace. You remove the trace. And in this variable, the equations simplify a lot. And in particular, if you have harmonic gauge, which in this variable, harmonic gauge can be written in many ways, but in this variable is this equation, this 4 equation here. Harmonic gauge is also called in different ways. Lorentz gauge, de Donder gauge, and so on and so forth. This different name for the same thing. So in this particular gauge, Einstein equations are box, the flat box. So if you want, you can put eta here. H bar minus 16 pi g c to the 4 t mu. So you see, these are linear equations now. We have linearized, so we got linear equations. And these are also equations that are very similar to those that we obtained yesterday with this relaxed, with this relaxed approach to Einstein equation. It's in the same gauge. So if you remember yesterday, we had this field. This is a completely general field. This doesn't have to be small. So within this notation and formalism, this is just minus h bar, okay? Well, plus correction. So the notation is consistent. We have, of course, Bianchi equation, which can be written in this way. And those simply imply the conservation of T mu nu. Now in flat spacetime. Okay, one could ask, I'm using heavily the harmonic gauge. So one possible question here is it always possible to specify, it's called also Hilbert gauge, by the way, is it always possible to specify to Hilbert gauge? Is a fair question, right? You may find a situation where you cannot. So it turns out that the answer is yes. Shortly, the reason is that if you make such a transformation, let's call it 1. On the h bar, the transformation looked like this. Plus box chi alpha. Okay? So what does it mean? That you can, if you make a if you have a generic gauge and you make and you want to make the harmonic gauge, then the algorithm, if you want to obtain the harmonic gauge, is to solve a box chi, say mu, equal a source term, where the source term is precisely minus d alpha h bar mu alpha. So if you can solve this, which is usually it's possible, then you can always go and construct the transformation that allows you to implement the coordinate transformation that goes to harmonic H. A standard result that usually is discussed at this level is to say, okay, let's consider, let's do it here. It's a weak metric. How do you obtain the weak, how the weak metric is obtained? This you probably have seen in the general activity class. One way to obtain is to say, okay, I have a static let's say, I have a static source of matter where T mu here is something like dt mu, so it's the vector that implements this static symmetry. And rho is a certain function, which is, of course, is the density, which means that notation there means that T00 is rho of x that does not depend on I, and it's compact support. We assume it. And that the other component are 0. So under this condition, you can assume that since the source is static, it's likely, or you can assume that the H bar is also static, right? Which means it does not have T dependent, which means that the box can be substituted with the nabla, and your linearized Einstein field equation are something like nabla H00 equal minus 16 pi rho, and nabla H rho mu I are all 0. These are not enough to solve. You have to say something about the boundary condition, but the boundary condition are simply that at large radii, every component of the perturbation goes to 0 because the source is compact support and because it's a deviation from Minkowski, so it's reasonable to assume this boundary condition. And you see immediately that under this boundary condition, these components are 0. The solution of this Poisson boundary value problem is 0. Whereas you see that this is nothing else up to a factor 4, the Newton equation. Okay. So from here, you simply get that our 0,0 component of the field is minus 4 phi, where phi is the Newton, or can be identified with the Newton potential. Then it's immediately to put everything together, and you can write down the metric, which you have probably already seen. And the metric writes 1 plus 2 phi dt square eta j dx. And this is the weak metric. Some comments here. So if you are very far away from the distance, from the source, your Newton potential will be something like m over r, right? And so you see that, well, you see immediately from here, or from the boundary condition that we have imposed before, that far away the metric look like with the gravitational potential, includes the gravitational potential 1 over r, so it's the Newtonian metric. The geodesics here are the usual Newton law. But if you go even further away, very far away, then you have automatically Minkowski or flat metric, as we assumed, of course. So as I mentioned before, the geodesics of this matrix is Newton's law. So it's the second derivative of the position equal minus the gravitational potential, the gradient of the gravitational potential. And here there's something to note, that, what is it here? That these geodesics are not compatible with this. Okay. These are not geodesics in Minkowski. This equation of motion imply geodesics in Minkowski, which are straight line. Here are geodesics with general gravitational potential, for example, the circular motion that you have studied. So this seems a bit odd, but is the fact that this simply reflects the fact that we are in a nonlinear theory and we are linearizing. So it's, if you want, it's a first iteration of a more complicated solution procedure. And essentially, you can use this to implement the curvature or to calculate the curvature as we did here. But then the resulting metric, if you go and study the geodesics, has different geodesics than the one that we have used. So it's an inconsistency, but is part of the fact that we are trying to solve a nonlinear equation. Okay? And finally, about this, there's a third observation. We can check whether it is good to use this theory in the solar system. So we can check what is the order of magnitude of h, which is typically, if you put inside the units, you have a c squared there. So these components, or the 0, 0, if you want, is the order, at least the order of, at most, the order of the gravitational potential. And this, for the solar system, could be g, solar mass, divided c squared, r. So it's this formula here, if you want. And this number here is something of the order of 10 to the minus 6, which is, yeah, it's much smaller than 1, okay? So this metric is good enough for the solar system, or for many things in the solar system. It is possible to do a bit better than that. I'm not doing it now, but you can, for instance, assume a stationary source, which is useful actually in solar system calculation and applications. In this case, instead of rho only in the T mu, you also have terms that are, for instance, I0. So you have this term. You can throw away the Tij terms, but you cannot throw away the Ti0 terms. And what you end up, so these are not anymore Poisson equation. But you see from this equation that you end up with something. So you have sort of 4 quantities in the T mu instead of 1. Instead of rho, you have rho and some spatial vector. But you see from here that what you would get is a sort of Maxwell equation. That's why it's called gravitomagnetism, gravitoelectric, gravitomagnetic effect, because it's entirely equivalent to solve Maxwell, okay, at that level. And it's important, for example, for studying things like lens steering effect and so on and so forth. So it's actually used. Okay. Let's look at gravitational wave now. So perhaps this was just a recap. So this linearized theory allows us to study in detail gravitational wave propagation. So in this case, we say that we are sufficiently far away from the source such that we can study the vacuum linearized equation. So again, far away. And well, in this case, of course, we have only box h mu equals 0. And if you have to just start with something, you can start with the plane wave ansatz. So you say h is some amplitude e to the I k alpha x, where, of course, this means omega t minus omega t plus vector k x. And you can start with ansatz and plug it inside here. What happens? Okay, here you have indexes and so on, but don't be afraid of that. It happens exactly as if you have the standard one-dimensional plane wave. So 0 equal box mu nu with the plane wave ansatz is simply k squared, which is this times h mu nu. Okay, so this is k squared as a 4 vector squared on Minkowski. So because you are taking two derivatives here. And of course, this equation implies immediately that k squared is 0. Which implies that the dispersion relation is this, with c squared, which means that gravitational waves propagate to the speed of light. Okay, so this is the first result, which is relatively simple and allows us to conclude a very important property of gravitational wave. There's another important property. You can look at the harmonic gauge. In this harmonic gauge, if you have the plane wave ansatz, simply write 0 equal the divergence of h bar. So this is one derivative of the plane wave, which is I k mu h bar mu alpha. Which also means that k mu times a mu alpha is 0. It's the same statement. And that's the second property of the gravitational wave, which is very famous, and gravitational waves are transverse. So if they are propagating along this k direction, the field oscillates in a perpendicular direction, so here. Okay. So you have already seen these things already in electromagnetism. These are the electromagnetic field has exactly this, the same properties. So it's useful at this point to count the degrees of freedom. So we have 10 equations. Equation, well, Einstein equation, okay? We have 4 equations for the gauge, okay? So we end up with 6 degrees of freedom, but that's not all the story, because again, exactly as in electromagnetism, if you make, so any transformation of this type, any coordinate transformation such that the displacement, the infinitesimal displacement vector satisfy the box, is also a symmetry, so a symmetry in the symmetry, okay? And so these, of course, are 4. So this is 4 additional gauge freedom, which in the end, so 10 minus 8, it's 2. And if you fix this additional gauge freedom, which again, by the way, it's the same conceptual thing that is also in electromagnetism, you end up with 2, really the real degrees of freedom that are not gauges. So gravitational waves have 2 degrees of freedom, which means you need two functions to describe them. So let me briefly discuss how to do this. It's relatively simple, so let me just sketch it. So you can parameterize this quantity, again, with an harmonic dependence. If you do that, this satisfies, if you do that, with k squared equals 0, if you do that, this automatically, it's an harmonic function, so automatically satisfies this. And you can fix, so this is first step, and you can fix the B mu, which are free amplitudes. For example, by requiring, so there are many ways you can do it. This is a specific choice. You can, for example, require 4 equations. One is H, the trace of H bar, which is nothing else but A mu equals 0. And you can ask also that 0 is, that these components here are 0, which again means A0I equals 0. So this is called a traceless condition. And this is called transverse condition. Okay, these are 4 equations. So you can make a gauge change, which will involve chi, so it will involve B. And so these are 4 equations for B mu. And you can solve it. Okay? You can solve it actually explicitly. But we don't need to do it because it's already kind of written here, okay? But this is the algorithm, again, if you want. If you want to move from a generic harmonic gauge to this gauge, which is called TT gauge. So there's an important comment here. This TT gauge, in particular this condition here, let's see. The TT gauge can be applied only in vacuum. Or far away from the source. And the reason is this condition here. If you have this equation with t different from 0, asking that h bar 0I is 0, is not in general a solution of this equation if t is different from 0. So you can apply that, or you can require this number 2 requirement. You can make it only in vacuum or outside the source. Okay. So this is also, for this reason, this is also called a radiative gauge. It's another name. You can think of it as the gauge that really just contains the degrees of freedom of the gravitational wave, and that's what we are interested in when you are far away from the source, and in some sense where you can define things, when you can define freely propagating gravitational waves. Okay? They're using an explicit expression, so comment 2, of h in TT gauge. What you do is you take k mu as omega 0, 0, k3, which just means you have propagation along the z-axis. Okay, you have k alpha x alpha, which is something like omega. Omega t minus z over c, plus minus a sign, but never mind. And then you can specify, so you take this, you can specify the Hilbert gauge and then the TT gauge, and what you find so if you impose this condition, what you find is that the A mu nu, so this is, if you want, the polarization tensor, is as a line of all 4 here, or all 0 here. You have a A11 component, A12 component here, 0, 0, and here you have A22. But A22, you have a trace condition as well in this. So A22 is actually minus, has to be minus A11. And then here is another 0, and on the other slot it is symmetric. Okay. So you see that doing this, you have just the 2 numbers that you want. You have a number here, or degrees of freedom here, and another degrees of freedom there, which of course is the same, goes also here. Huh? So the only non-zero entry in the subdiagonal part is this A12, which is also here. And typically what one does, say, okay, for a reason that will be clear soon, I call A plus the A11, and I call A cross the A12. And with this notation, I can call H plus A plus E to the I omega T minus ZC, and H cross E to the I omega T minus ZC. Okay, and well, you do want real gravitational wave, so you can add here complex conjugate if you want, or decide to take the cosine. Just take the cosine. And so with this definition, what you end up is you have H mu nu in TT gauge, which is a matrix that has all 0 here. Yes, here it has exactly, it's the same as that. This is all 0 and this is 0. And here that the cos, so e to the I omega and so on. So this is done, or well, it can be done because I skipped the passages, but this is done explicitly by assuming this wave vector in this way and simply using the equation that are there. But in general, you don't do that way. In general, so comment. In general, you obtain a solution for H bar in harmonic gauge. And you make a projection, you make a TT projection using a tensor that is usually called lambda. Let's say alpha, beta, it has 4 indexes, mu nu. This is a special projector that precisely projects, if this is generic K, this, and you're looking at here, this tensor precisely projects any harmonic harmonic gauge solution to far away from the source to the plane that is perpendicular to the direction of propagation. So it's called lambda and K or N, and you have constructed this explicitly yesterday, as far as I know. So in practice, you don't have to go every time through these explicit passages. There's an automatic procedure. Once you have your solution, say within your post-Newtonian theory and so on and so forth, in an harmonic gauge, you take that, you project it in the plane, you automatically project it in the plane perpendicular to the propagation, far away from the source. Yeah. Yeah.
So you mentioned that only in the radiative case you can use this gauge, especially you can use the transversality. But does that mean that if you're close to the source, the gravitational wave has more than 2 degrees of freedom? Or that
It's this particular, so it's this particular equation that that you cannot impose.
you cannot impose that?
Because of the reason that I discussed, because you have this box.
Yeah.
And so on, so 0 would be second derivative of 0 equal T mu nu, which is different from 0 in general. But the degrees of freedom are 2. Yeah.
But it's not transverse. I mean, the plane of oscillation is perpendicular to the direction of propagation.
Yeah, you would need to, so the transverse condition is this one. And to derive this, we only needed the harmonic gauge. So it's still transverse. But this particular, if you want, representation, where you reduce to H plus H cross, in this way, this is valid only far away.
So you still have the same properties, but
Yes.
the composition of the PT gauge.
Yes. This particular construction, which is one that we use, is not possible close at the source. But it's also not useful there because it's the thing that you need to isolate the wave once it is detected, if you want. Okay. Okay, so let's recap what we have done so far. Let me see. Okay, I think I can delete this. Okay. Yeah, so what we have done, we have discussed the propagation, so we have put ourselves in a situation where we are far away from the source. We have made plane wave ansatz. The equation is linear, so combination of plane wave is also solution. So it's fine what we have done. We have derived that waves propagate at the speed of light. That's an important result. That they are transverse. That they have 2 degrees of freedom. And we have given a particular gauge in which these 2, say, degrees of freedom are clear and evident, and they are there. Okay. So at this point, you may ask, okay, what's the difference with electromagnetic waves? Because all these properties are in common with gravitation, with the electromagnetic wave. So in particular, light speed, it's checked. The transverse is checked. The 2 degrees of freedom, it's checked. And in fact, if you look at Maxwell theory, you have, for instance, you have an equation like this. Let me call it. And if you look, if you write it, this is Maxwell tensor, Faraday tensor. If you write it in terms of the vector potential, and you get the index right, it doesn't matter here, but you should get them right. You get something like box, A nu, minus a quantity that is like that. And typically what one does say, okay, I still have gauge freedom, I can make this equal 0, and this is called Lorentz gauge, so our gauge, and you get box A, okay? No. And then you go and you can repeat these things. You have one index less, but everything. So where's the difference? In short, you can define something that are called a LCT amplitude. And yeah, so for gravitational wave, this is called, well, you can write it A plus, let me write it this way, A2 plus minus. It will be clear why there is this 2. But this is simply the A plus polarization, so it's a combination of the 2 polarization. So okay, now I call it small a, I could call it large A there, but it's the same. So this is for a gravitational wave. But then you can do the same for electromagnetic wave. In this case, I will call it A1 plus minus. And for electromagnetic wave, as I said before, you can repeat the entire thing. And this 4 vector boils down to 2 components. If you are propagating along Z, let's say these are AX minus plus I AY. But the discussion is completely analogous. But then, and so we are in this situation here. We have an XY plane, Z, and the wave is propagating around here. Both waves are propagating around this, so they are oscillating in this plane. And then you can ask, okay, how about if I rotate the fields around Z of an angle theta? So you make a rotation like this. And what you find out is that the A, let's say A prime 1 plus minus transform like e to the I theta A plus minus 1. And if you do the same for the gravitational wave, the transformation has instead the 2. Okay, so here is the difference between electromagnetic and gravitational wave. There is a field that transform differently under rotation, and in general, a field of spin S would transform as e to the is theta under the same conditions. Okay, so there is where the difference is. Okay, am I going too fast? Just say it very in case. Okay, what I want to discuss now is the effect of gravitational wave on test masses. And I'll start with an example. The example is the following. We take two test masses, let's say at point P and at point Q, that are separated by length L naught initially. And then we say, okay, now there's a gravitational wave that enters the blackboard in this case. And so it will have an effect of stretching these test masses somehow. This is at least what we expect. And we want to calculate what's the effect on these test masses once the gravitational wave has passed through. And one way to do it is to look at the space-time diagram and say, okay, now I have time, I have space, say three dimension. And I have, this is the P word line, this is the Q word line, this is TP, this is TQ. How do you measure this distance? Well, one way to measure the distance is to ask P to send a light rays to Q, to ask Q to send it back. And the distance will be half. Will be related to half of the half of the time. So you measure the distance by measuring time. Okay, half of the travel time that the observer P gets. Okay, so we say that the coordinate of xp are the origin. We say that the coordinate of xq is initially L0 and I, where Ni is this vector here. So it's a spatial unit vector. And of course, at T P equal TQ, you have that L square is delta ij, so you have flat space-time, qi, qj. This is called, by the way, this is called the radar method. Landau, Lifshitz discussed this. And then you look at T prime, and you calculate L square. There was something that I forgot to, okay, I'll tell you later. And this L square is G nu x mu q prime minus p prime x nu q prime minus q prime nu. But here you say the time are the same, so I can simply switch to a spatial coordinate. I will comment about some of these choices that I'm making. Wait, this is P. So, okay. Yeah. But this is 0, because I decide that. So I have only Gij xiq coordinate, which is L naught and I. And so I have L naught square, Gij and I and j. And now the thing that I forgot to tell you before is the expression of the metric entity coordinate, which is simple, but I should have given it. Yeah, it's simply eta plus, but I wanted to write it down once for all somewhere because we will need it also afterwards. So let me write it here. Yeah. Okay. So G entity coordinate is minus dt square plus the spatial part is h dt ij xi xj. You could see from the matrix and so on, but this is just, we have it somewhere. Okay. So now what you do is to substitute here this metric and so you have delta plus h tt ij and I and ij. Okay. So all in all, what this means that if you go and calculate dl over L, which is the relative variation of this distance at the passing of the wave with the radar method in harmonic gauge, entity gauge, it's L over L0 minus 1, and you can work out from this expression, you have the square root, because there is an L square here, 1 plus h ij tt and I and j minus 1. Okay. If you now expand, so h is small, because gravitational waves are tiny. If you expand this, this is 1/2 h ij tt and I and j. So this is the formula that yesterday I used to convince you that gravitational waves are very challenging to detect and so on, because that's what you have to detect, because if h is very small, you remember 10 to the minus 20, 10 to the minus 17, 10 to the minus 21, or so on. This is the relative variation that, for instance, interferometric experiment have to measure when the gravitational wave pass.
So what you call the strain is basically
Yes, what I call, it's basically, yeah. Or if you want, yeah, it is the combination of the polarization of the the polarization in the TT gauge, the, combined with the geometry of the system, because there are this n inversor. Okay, so this is fine. It doesn't fully apply for an interferometric experiment because, in fact, this radar method is correct when these masses are small, are close to each other. This calculation also uses the fact, an important fact that I'm just saying, not working it out, but that the TT coordinate remain constant during the motion. This is something that I've used here, and it's something that you can prove at order h. Okay. And the other comment is that, as everything, distance measurements are always time measurements. Okay, so remember this. When we measure gravitational wave, we don't measure difference in distance. We measure difference between clocks. Okay, so this sketches how test masses interact, how gravitational wave interacts with test masses. There's a proper, more formal geometrical way of discussing in general this. This is what I'm going to sketch here. So the geometrical way instead of using this radar method, is to use the geodesics equation. And the geodesics equation is like this, and I will define the symbol quickly. So it's two derivatives. This is the covariant derivative. I will tell you what the U field is. It's a vector, but I will tell you exactly what it is. So this is a second derivative. There's an S, and it's an equation for an S vector that involves the Riemann tensor. So this is Riemann. S, which is the unknown in this equation, it's called the displacement vector. And U is the tangent vector to the word line. Okay. So just to quickly refresh, I'm not going to go in detail into this equation, but I need to show it. If you remember the GR class, you have some word lines, you have a vector U, and what this equation, so these are trajectories, okay? What this equation tells you is it's an equation for S, which you can visualize in this way. And it's a tensorial equation for the relative motion, in quote, between these word lines. Okay, so if you know the Riemann tensor, you can calculate how this word line gets closer or away from each other. So it's the proper geometrical tool to study this type of problem. Okay. And of course, the game here is to go through, linearize everything. Okay, so you have to linearize the Riemann. You have to, of course, you will assume TT gauge and so on and so forth, and go through all the step to specify this equation for our gauge and our case. And what you find in the end after these calculations, you find that ds, this becomes simply a derivative. Let me directly write it for the spatial components, which are the relevant one. Yeah. So I have a typo here. I think the right combination of the Riemann is this. J. Okay. So you can simplify, in particular, this U in the case of the T gauge and to order H. You can simplify this covariant derivative, and you arrive at an equation like that, and then you have to plug in the Riemann, which is linearized, but this is very simple. Yeah, as I said, there's a yeah, this may be correct. Yeah, what you end up, it's that the Riemann in this gauge and approximation is simply the second derivative of the metric in T gauge. Okay. And now we want to solve it. And we want to solve taking as initial data a certain initial displacement between the two masses, which we call it S naught I, and S dot I at t equals 0 because the masses are initially not moving. Let me do a further approximation. Here, I already have H, or quantity order H, okay? So, at that order, I can simply substitute S, in the variable which I'm solving for, with the data that I have, okay? Because it will be S as equal as 0 plus something that is order H, but here there is already H. So at first order, it's perfectly fine to put S naught there. And this is correct to this level. And so I can solve it on the blackboard very, very easily. The solution considering that the velocity is 0, the solution is Si of t is Si naught plus 1 half htt ij S0j. Or if you want, delta ij plus 1 half htt ij as naught j. And I can specify for the z direction so we said before that if I have a wave in the z direction, this is oscillating in the xz plane. So that's all I need, x. So the component of this or the x component of this displacement, I call it x, and the y component, I call it t. And this is, now I'm just rewriting the thing above with slightly different notation. So I have plus y, because this is a slot below, and x. Okay. This is the equation that I wanted. Now let's consider this scenario. We consider only the plus. So we say that cross is 0. And we put a ring of masses in the xy plane. So we will have x naught, y naught is r naught, which is this radius here, cos theta, cos phi, sin phi. And with this, we can write that the equation here are x of t equal r naught 1 plus h plus cos 1 minus h plus sin. Now we are almost there. You can square this equation, sum them up, and what you obtain is 1, because you have cos plus sin. But here you have x square, r naught square, 1 plus h plus square, plus y square of t, r naught square, 1 minus h plus square. Okay, so now you see the effect on the ring. If you have a plus polarized gravitational wave hitting a plane xy, which is the blackboard, you see this is an ellipsis where these denominators here are the semi-axis. And so imagine now that h plus is a sinusoidal function of time. The semi-axis of these ellipses are oscillating in time. And this, say, if this gets contracted or elonged, the other does the opposite because there's a minus sign. Okay? So this is an equation for the ellipses in which the semi-axes are changing in time, but in a way that if this increases, this decreases, because it's the same quantity with minus and plus. So if initially you have your perfect circle, the plus polarization does first something like that, so shrinks the masses. So dashed means without gravitational wave. And then it goes back. And then it will shrink the other way around. And then it goes back. And this is a 2 pi period. So this is pi half, this is pi, this is 3 half pi. So now you see why I've called this function h plus. It's because of this, okay? So if you have the gravitational wave entering here, it squeezes, then it goes back, and it gets enlonged, and then it goes back, and it cycles this way. Okay, so this is the effect of the plus polarization. You can repeat everything with a cross. If you take the cross polarization, you put a ring of masses and so on. Now, this you have to keep, and you throw away the plus. This is slightly more difficult because now, at the right-hand side of this equation, the system is not diagonal. You see, you have x, and you have y naught. Before you have x naught. And here you have y, and here you have x naught. So it's not a diagonal system as it was before, that was only depending on x. But this is simple, it's a 2 by 2 matrix. You can diagonalize. The matrix is, so the right-hand side matrix is 1, which is the x naught, cross alpha 1. You can diagonalize this, which amounts to actually a rotation, okay? But this is a rotation of an angle pi fourth, okay? This diagonalization, and so what you have with cross, well, you have exactly the same, because you have diagonalized, because in a frame that is rotated pi 4, this matrix gets identical to that one. And so you have the same thing, but rotated 45 degrees, which of course makes cross. So you start with your circle, and then you have something like that. You go back to the circle, then you have something like that. Then you go back to the circle. So this is the effect of the cross polarization. Which is rotated for 45 degrees. Yeah.
I would say that the main difference with the electromagnetism is precisely this. Even if you have one polarization, for example H plus, there are two spatial coordinates that are affected because of the quadrupolar nature.
There are two coordinates
that are affected by the wave, say, because the rotation of x and y, if you have a plane electric field, say, always in the x direction, this is the only.
But if you have electric field, you have oscillation around x and y as well.
And plane polarized wave, the electric field is always in the same direction. So is it really only the main difference that the spin equal to, or the quadrupolar nature can also be seen from?
I mean, you can see it also, yeah, if you want, you can see it also from here. So you have this, yeah, you have this pi fourth, for example. It is not there the same way. And what you can imagine is, so you can take the same, for instance, you can take the same polarization vectors of the electromagnetic wave, right? And you would have A mu. You can take two of them, build A mu, A nu. This would be for the gravitational wave. Okay. Yeah, other questions? By the way, ask a question. So I'm basically done. Maybe I went too fast, but I'm basically done with this part on the weak field. Not sure if
you can always combine plus and minus. plane different lines, like you do for
Yes.
finger, black and white polarization.
Yes. Yeah, yeah. In general, you have this is the general situation, and then what I've been showing is simply the single effect of the single pieces. But in general, this is, you have the two, and you have to combine them, and you have to choose your let's say the geometry of your system, of your test masses, whatever. In such a way, in general, you have a combination of H plus and H cross. This is what it is done in the interferometer. It's in general, it's a not complicated. I would not say complicated, but it's a geometrical combination of the polarization that depends on the particular orientation of this interferometer, for example. Yeah, let me see if I want to add something, but I would say no. I think it's a bit early, but I think I can stop here. And yeah, what I want to discuss tomorrow is the concept of energy, and tomorrow, yes, and the concept of a stress energy tensor or gravitational wave. Something that you have started to look and work with, in particular this power or luminosity formula that you have been using. So I want to arrive there and justify this. And then we'll continue with the sketch of some more advanced topic. And, yeah, thank you for listening.